3 years ago, I believe, I was here giving a short, not so short talk about all that was new about the modules that I produced, etc. And it was way too long, right? So the good news is today we have a much shorter, contained, confined conversation. Okay? So that's good news to begin. And hopefully you are all awake. I am waking up at the moment, so probably we'll get warming up as it goes on. The title of the presentation today is a bit intriguing. It's towards visual focal plus, as Sylvain liked that. And the idea was, we have been talking about the same thing, rehashing the same features, extending them, tweaking them, and making extensions to the same old crap for years, right? So, can we talk about something slightly different, better, that has not been done before on the 41 platform? And I believe that's the case, because we're going to be talking about, is not CAS or CAS, but it's approaching it. It's getting into more abstract kind of language, easier to program. Of course, that means nothing to people like you guys, because you know RPN inside out, and you can do anything on RPN. But some people also feel intrigued about, oh, we have new instructions like do while, for next, if, then next, and if, things like that. So it gets closer to a more higher level language, okay? Call it a pastime or a totally useless pastime or whatever, but it is what it is. It was a good challenge to do it, and hopefully I remember it good enough to tell you about it today, because this kind of software is very weird, even for the person who designs it. So as I said, we have a more contained or more concise agenda today. Is going to be about, I'm not sure if I should be looking at there or here, but it doesn't matter. I don't see either. So the formula evaluation software, which is the ability, the engine, which is going to allow us to type a formula on the 41 alpha screen, hit the evaluate, and we will get the result. So that's called the formula evaluation. That happened a couple of years ago, and I have been extending it little by little. So I added a script language. So you can do that both things manually on the keyboard or interactively, or you can program the instructions into an X file, X memory file. So it just runs as a batch file, so to speak. The latest addition to that system was to add what I call the, how do I call that? The conditional structures, okay? So this is the do while, if, else, and if, and select case, case else, and select. Again, you know, this is like crazy. Where are the news? This is no news, right? But on the 41 it's kind of funny and kind of fun as well. And if we have time, which I doubt it, I have a couple of appendixes, the codas. We see how it goes. You are free to ask questions anytime. I don't mind being interrupted. And on the other hand, on the contrary, I like it. So let's go through that. And before it gets too late and I don't have time to give thanks to people who deserve it, this is the thank you slide, right? So, and you will recognize the usual suspects here. And we are happy to have a few of them here today. We have Mindert. I'm pretty blind, so I don't know where you guys are, but Minder is here, Sylvain is here, and anybody here on that list, but you know who they are because we all have been here, bought the t-shirt, and know what it's like. Okay, so that was the thank you slide. We are done. Thank you for your attention. This is the first part, which is the formula evaluation ROM. And I like this quote from Arthur C. Clarke. Because when I was preparing this presentation, I didn't have an idea how to explain this because it was weird. I didn't understand how can this work? This code makes no sense. I don't understand how this works. This doesn't work. But all of a sudden you have to go into the code and you realize that when you wrote that, you must have been in a catharsis because it was very weird. But anyway, any sufficiently advanced technology is indistinguishable from magic, right? And the people like me who program these things, sometimes it's like magic that the 41C with these addition ROMs is capable of doing this interesting tricks. That's a conceptual block diagram just to explain the basics. So what are the basics? The basics are I have developed an evaluation engine that takes the information from the different registers available to the calculator, like the stack, and data registers as well. It's not here shown, but data registers can also be taken as input data. And of course, the key component here is the formula that is typed into the alpha screen. The evaluation engine is going to read the instructions from alpha to see what has to be done, pick up the appropriate register information or values as the formula instructs, do the magic, and put the result into the right destination. The destination could be any register on the stack, or any data register, or buffer registers. So we see that there are a few concepts already here, which is important for you to notice. There is buffers galore. There's a buffer number 6, which is used to do the intermediate calculations. And there is buffer number 7, which is used for the buffer registers. In addition to the 4 or 5 registers in the data stack, X, Y, L, Z, I think I'm forgetting one, X, Y, Z, T, L, there are 5 or 6 more registers in a buffer. That's buffer number 7. And they are labeled A, B, C, D, E, F. So we have 2 buffers. One is for data, buffer number 7, and one is for the intermediate calculations, which is buffer number 6. So that's it. It's quite simple, right? Of course, the devil is in the details. You need to understand what this thing does, which I barely do. And then once you understand that, it's simple to put all together. All right. An introductory slide here. There are a lot of new, how to say that? There is an overlay which is used for formula entering. So you need to enter the formula in alpha. You would say, well, what's the big deal? You just press alpha and type your characters. And if you know how to do that, it's perfect. There are a couple of tricky characters like the parentheses, like the curve parentheses. And those are not standard in the alpha keyboard. Now, of course, you can say, I can use the CCD or whatever OX extension module, and that gives me access to all these weird characters. Fine, you can do that. But if you don't want to, plug in another module. The formula evaluation module comes with its own formula editor. And the formula editor allows you to type anything that the formula ROM can process, okay? So don't be put off by, oh, how do I enter this formula into alpha? Because it comes with its own formula editor, and that's fine. Here's a couple of examples of the type of formulas that you can have. They're very useless, right? Because, for instance, the first one, what it does, it gets the 3 trigonometric functions, sine, cosine, tangent, and then they do the inverse functions as well. So at the end of this line, you just get the sine and the cosine, tangent of x, and then you do the inverses. So at the end of this day, you have the same x that you started with. But just an example of you type this formula, you press evaluate, and then it gives you the result. Another example is the logarithm of the exponential of 1, that is equals 1, right? Then you have here, it's hard for me to see, this funny alien sign stands for pi. So pi is also another variable which is directly typable or keyable into alpha. And here you have an expression which is the decimal logarithm of y over 2 plus pi cube. Beautiful, huh? And then here you have the discriminant of the quadratic equation, of course. So you can just type the discriminant and either calculate that or use that as a step in your program to calculate the roots of a quadratic equation, okay? So the idea is that you just type the formula, you don't need to put RPN steps, you don't need to worry about where these things are, because the name of the variables tells you what the data is going to pick up from. If you type an X, it's going to take the data from X. If you type Y, it will take it from the Y register, and so forth, so on. There's something more here. This is an example of what's in buffer number 6. So how does this thing work? How is it possible that this thing works at all? Well, this was developed or designed by Greg McClure. Greg and I put together the formula evaluation module, and his idea of the buffer was a genius idea. So Greg, if you are listening, thank you very much again. I'll give you half of the revenues. Of course, it's zero. Half of the proceedings of this meeting is going to go to Greg. Your check will be in the mail. All right, so here is where a lot of stuff, actually everything that is contained in this formula will be pushed into this buffer. It's a last input, first output buffer. So what goes in there? Well, it's going to get instructions of what to do with the data, plus the data itself. And I'm not going to get into the details, but the buffer contains different types of data. It contains BCD values, which is standard decimal values. It contains flag status codes, which tell us what to do with the operations, Those codes are going to be computed based on the instruction codes or the instruction names. Like LG is going to be a decimal logarithm. That's going to trigger, it's going to go to a table, going to read the codes, and going to input something for the buffer 7. So the first thing the formula evaluation engine does is reads the formula from left to right, codes everything in, pushes everything into the buffer. Now that I have everything into the buffer, it goes the other way around. It starts calculating the values from the buffer. So it reads the formula back from right to left, right? And it starts doing things a chunk at a time, pushing and popping values from the buffer as needed. Simple. There are other instructions, which we will see them later, that not only you are supposed to input a formula and get the result, you need more tools to be able to operate and manage all your needs. So one of the tools you need is, okay, I need to store this formula somewhere in memory. So I can just bring it back later if I have to reuse alpha for other uses, right? Or I also want to input the formula that I have in alpha into the program memory. So, you just type the formula and that goes straight into your program as a program step or 2 program steps, depending on the length of the expression. So you have functions like recall $, STO $, and swap let get to get values from the buffer 7, A, B, C, D, and E, as I said before. And the beautiful one here, the funny one, is A to PM, which is from alpha to program memory. That does the dumping of alpha into a nice, shiny, and beautiful program step. Magic. I said before, magic. Okay, so here are the syntax. And of course, some people here may like RPL, like I dislike it. And RPL was born with the 48. And I remember when I purchased my 48 initially, which I was trying to just, I know how this works, right? I have no idea. And all I could get out of that machine was beeping. Ping, 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 syntax error. So this module comes with its own syntax error message, which means that if you type anything which is not in those 2 columns, at the time of the evaluation, you're going to get syntax error. So if you like the 48, this is your module, guys. You need to try this. All right, so what do we have here? We have conceptually 3 things, I believe. What do we have? We have variables, and what are the variables? Basically, it's another fancy name for your data. But the variables are named, so your data is named. So you have X, Y, Z, T, and L on the stack, plus A, B, C, D, E, F on the buffer 7. So you have 10 variables, and you can use that variable name into your expression. Then you also have control characters. Control characters are things like sigma, P, etc. And we will see what the sigma is for, but as a heads up, is to do summations of things between brackets. So you can do loops just by having the sigma as first character of the expression. No, you don't need to worry about having a label and a goto, ISG, etc., or DSE. All that is a thing of the past. This is called Visual BF for one reason, which we still haven't found out. Then you have all the mathematical expressions somewhere here. Some of them are a bit not so intuitive, like tangent is an N. And why is that? Because we ran out of the TNA. The TNA were taken already. And I didn't want to use long expressions, because if you remember, alpha is capable of holding up to 24 characters, no more. So the shorter the name of the function is, the better, because you can stuff in there more longer formulas. Now, having said that, you can indeed chain two different screens, okay? And how you do that? Well, you just do first one calculation, a partial calculation, and then you put the result of that calculation into another data register or variable, and you make another expression that reuses that result as an input, okay? So you can do that multiple times. You can chain different formulas. And we will see an example with gamma, the gamma function. Okay, so you also have the ability to put integer numbers into the formula, or integer digits, up to 9 digits together. Now it's a waste of space, if you ask me, because you use up many characters in the formula. So you'll be better off by having that number into one of the variables. You assign that number to a register X or Y, and then all you do is just put that register's name into the formula. But if you want to multiply by 2, by 3, or divide by 7 or 77, you can write that directly into the formula as well. So numeric characters go there, then you have the different formulas: absolute value, integer part, fractional part, square root. I cannot read this. Is this focused? Is that not focused? Okay. I was thinking it was me. It is me too, but it doesn't matter. Anyway, so you have all the trigonometric functions, hyperbolics, and the usual suspects: arithmetics, logarithmics, all the explicit functions. All works. They're all using the 13-digit routines in the OS. So the accuracy is quite good, despite all this data movement back and forth between buffers, etc. We don't lose any accuracy almost whatsoever. So let's keep going, because now we're warming up. All right, this is another way to summarize what this thing can do. That's the overlay that gives you access to all the formula editing. You can input your formula in alpha. Once you have it in alpha, you can just use these two functions, sto $, and recall $. So you can store your formula in memory for reusing it later. So you can reuse alpha, write something else, and then wipe that out and bring your formula back. No need to retype it. Or you can just store your formula into program memory directly. Once you have done all that, it's time to evaluate what you have written. And that is, you have what is it called? A launcher, a function launcher. And this function tells you where do you want to place your result. You can put it into X, Y, stack registers. You can put it into any buffer register. So if you press the B, then it will open up with which one of the buffer registers you want. And then R is for data registers. Input the number of the data register where you want that result to go. Trivial, easy, convenient. Right, so all I said is just repeated here. Buffer 7 is using the destination of the data, and chain calculations are allowed. So you can keep asking or doing the same thing over again. Okay, another way to summarize this is by functionality. And here we have the first box in there has to do with not only you can do one formula, but you can do a loop of calculations as a summation. So you can put the general term of a series or the general term of a product, and then specify from and to values to that summation or product. So from 1 to 7 or from 1 to infinite. Infinite is also allowed. Of course, it's going to just keep doing the same calculation until the different partial results are equal, as we all know. So then you just stop doing more calculations. So that's what the sigma is for, eval sigma and eval p. Eval sigma and eval p are independent functions, but eval $, can also understand those characters. So you don't need to remember that there are 3 functions. You can always use eval $, to do any of the single calculation, summing, or product. Then we have something interesting, which is going to open the door to the conditional structures, which is eval ? So you remember the functions like is x equal to y, or is x equal 0? Those are very good testing functions that check the value in your x register and compare that with the value in the y register, and skips one line if it's false, or continues if it is true. Very simple, And we all know that very well because we have used that thousands and thousands of times. But what if you had the capability to have two different expressions, like square root of x plus y over t, logarithm of pi, and on the other side you have another complicated expression, and you want to compare those two expressions. So it's a generalized testing function, and that's what eval ? Does. You have two formulas, and it compares the value of the results of both formulas and acts according to your comparing instruction. It could be less than, equal, greater than, or different. Okay? So why is that important for the conditional instructors? Because that's the foundation of the if and the do-while conditionals. Because if something equals something else is what we want. Or do something, keep doing something while A is different from B. Or keep doing it while B is different from R. Okay? No questions? So it must be clear. All right. And then we saw that before because it's the same as the previous slide. Is the evaluation dollar what tells you where to put the result. All right, so the formula evaluation ROM comes with that powerhouse tools, but it also comes with its own example library. And the example library, I call it the formula evaluation applications. And those are canned examples of how to use those tools to solve these problems or to do these calculations. And you see there is a long list of them. Some of them are very well known. Very simple, it goes from simple to more complex. Vector distance, 2D and 3D distances, which is quite trivial. And it gets more complicated when you just go into the right side of the slide, when you have more special functions like gamma and Basel functions, etc. But it's all using the same formula evaluation engine. And if you look at those programs, oh, thank you. My lovely assistant. Now I have to drink, otherwise he gets pissed. Do you have a question?
Yes, please. What about the execution speed?
The execution speed is quite fast. It is, I think it's 95 to 97% of plain RPN. It is quite fast. Now, this is a very good question, but I got spoiled because I use the CL all the time, right? So, but I did measure it, and it's about 95 to 97% of the just plain RPN listing. Because the RPN listing does more things. Every time you do an RPN instruction, the operating system has to read an instruction and doesn't do it. The formula, you have to write the formula. Okay, this is a long discussion. 95 to 97 discussion. Okay? We will have an example. We will look into the details of how to program the root finder using solve, using the second algorithm. So you will see how trivial it is and how much easier to read the code is. If anything, guys, this is the advantage. If you look at the RPN listing, it's horrible. To deconstruct all that crap, you need to know, first of all, what is the first expression? Where does it come from? Where are you putting the registers? What do you mean by R24, recall, store? What is this? Now, on the other hand, this thing is giving you the formula, executing the formula, and much easier to read. So if anything, this is the biggest advantage of this module. I'm seeding the path for more things in the future. Right, another two examples. The first one on the right, on the other right, is the Lambert function. Lambert function done in, it's actually not 18 steps because there are 4 steps here doing a round comparison, just to be safe. But if you remove these lines 12 to 16, it's a quite short and compact way to calculate the Lambert function. So how is it done? It's nothing mysterious. You get the formula, which is available everywhere, somewhere here, and you just type this formula. You don't type it literally, but you just type, you say, okay, where is going to be the previous value and the next value, you call that x, y, and you type the formula and you run it. On the right side of the slide is a more elaborate example, which is the gamma function using the Lanczos formula. And here you see that we have a product in the denominator. So that product is going to use eval p somewhere. And here you have it. You have an eval p. So you type what's inside of the product, including the limits from 2, and that is one component of your formula. You put that result into another register, and you reuse it to type the more complete formula that has a sum. Why is a sum? Because you have 5 different characters. You see the sum sign here. And where are these numbers? These numbers are in the buffer registers. So that's why the first thing this program does is it populates the buffer register with the right constant. And then it reuses the names of the registers into the calculations. All right, so we are now getting into the interesting part, because I think 2 years ago, 3 years ago, that was more or less done, but this is all new. So now we have the ability to type formulas and get the results. Good. We can have sums, so it loops around between a beginning and an end, which can also be infinite for series. And we have the ability to compare 2 general algebraic expressions and act in consequence. So that's it. Now we are ready to do things like make a do-while. So keep doing something while a condition is true or is false, or just test directly for a condition, and based on the true or false, based on the Boolean result, go to different sections of the code, if, else, and if, or test for a condition and have multiple choices, not like else, if and else and if, which only has 2 choices, but if you have a select case and case else, or case A, case B, case C, you have different multiple choices, which is the select case and end select. And that's what we're going to be looking next. All right, so here we're getting into the under the hood to see how this works. These are new functions. They are HP-41 functions, and they are in catalog 2. So one of them is called select. It's a prompting function, so it asks you which register is going to contain your markers or your flags. So select 5 means, okay, I'm going to use register number 5 as a marker to see what happens with the values that I am going to be proposing to this marker. If the value in 5 equals any of these markers, and the markers are called case, let's say there is a number 3 in register 5. So I go and say, case 4, don't do this, because this is not the value in register number 5. Case 4, case 5, no, don't do that either. But if I go to, suppose there is another one which says case 3, yeah, this matches the value in the marker. So I'm going to run that segment of code. So what the OS has to do is goes to the beginning, and say, oh, all right, I have a select instruction, so I want to look at the argument of this instruction and see what is going to be, which one is going to be the register to monitor. I put that register number into the buffer header, and I also put whatever is in this register value to be compared to later in the next case statement. So it keeps good. I also activate the structure flag to make sure that I know there is a case structure active. All right. So the next instruction the program sees, or the OS sees, is case. All right, so I have a case instruction. I need to look at the value of that marker register and compare that with the case that I have in this case. It is the same. Then I'm going to run the instructions right underneath case until I find another case instruction. So that's done. I've done all my case 3. There's another case. I'm going to jump to the end of the select case structure. Okay? That's why it's very important that the select step looks for an end select down the hill or down the river, because otherwise you don't have structural integrity of the structure. You need to make sure that there is an end select whenever you find a select instruction. So that sounds like science fiction a bit, but if you think about it, when you type an RPN program and you compile it, the OS already knows how to do that because you have the go-tos, and the go-tos, when you compile the program, they are looking for the label, and it stores the distance into the go-to step. So when you run it, it jumps directly, it doesn't have to look for it. So in this case, it's the same thing. You just have to scan the code, and when you find a select itself scans the program underneath it, looking for an end select. If it doesn't find an end select, it's going to show you the no bound. Something is wrong. You need to bound that structure. It's unbounded, right? So how does this thing know that the case is being done? Because when you get your match, if you find the right value which is contained into the marker register, the structure is deactivated, boom, as saying, I've done my task. So the next case structure is going to say, oh, the structure is deactivated, so I don't need to check at all, and I'm going to go directly to the end select, which I have stored the address of the end select into the buffer header. I hope I haven't lost you. Are you with me? Somebody say something. Is this a dream? Am I dreaming? All right. So that was the most complicated. Actually, no, that's actually one of the simplest ones. The next one is for next. And you say, come on. Why waste our time with this? We have ISG and DSCs. Who hates ISG and DSCs? I hate them. Because now I have a very similar functionality, I admit it, but it's much easier to manage, to handle, to process, to program, and to read. Which is, all right, I get a for, which is also prompting, and the prompt contains another register. So it's which register is going to have my control word. And the control word is from a beginning register, from a beginning value to an end value, and the step size, which is of course the same as for I equals 7 to 25, step 17, or step 1. Same syntax as you find in BASIC for the for next. So what we're doing here is we just translate that or just rehash that and say, okay, we're going to put a for register. The register is going to contain the control word. And for is going to look for a next instruction. Again, always we need to do a conditional integrity, structure integrity test. Because if there is not any next downstream, for, or is not gonna, will not know what to do, or the OS will not know what to do after to do the loop back. So how do you know how to loop back? Well, you need to store the for address into the buffer header. So when the execution goes sequentially and hits the next is going to compare the current value of the pointers with the actual conditions from to. If it's not done, it needs to iterate back, so it will jump back to the for instruction and repeat after increasing the current pointer in the number of steps defined by the S steps. I think this is simpler than I'm making it, right? So basically it's a for next loop. That's it. It's a for next loop, and that's how it works. Now do while and if are more interesting because they involve the generalized expression comparison. Let's go first with a do while. I do a do, and then what it does is always check the structure is complete. There is bounds to it. So do is going to look for a while. If it doesn't find a while, no cigar. You need to have a while, otherwise you get the no bound. Okay, so I've done that. I checked that. There is a while somewhere down below. And it doesn't do much apart from that. Yes, it does. It gets that its own address into the address return stack. So here we are not using the buffer header. Rather, we are using the return stack, the RPN return stack in registers A and B, if you are familiar with those. And the reason why we are not reusing again the buffer header is because we want to be able to combine do whiles with select cases and for nexts. So we cannot be overriding the thing that we already used, right? So it's possible to nest structures. You can nest a do while and a if and if into a select case structure. And to be able to do that, you need to use different repositories for the markers and the pointers, okay? But that makes it very, very interesting, because you need to manipulate the return stack structure for registers for RPN. So it's nothing to do with your M-code return directions or addressing. That water had poison in it. You all are witnesses. So she wants my insurance. All right, so the key point of the do while is what happens when we hit the while instruction. And that's the real contribution. All right, so I'm doing something because I had a do instruction, so I'm just happy, just turning around doing it. And then I find a while. Okay, well, so while what? Then I look into alpha, and alpha has to contain the conditional, the Boolean instruction. We'll have basically two parts. I will execute the left part and the right part, compare them, and according to the instruction that I have, greater, less than, equal, different, I will do either go back to the loop, to the loop back to the do, if it's not true. If it is true, sorry, because it's do while, so keep doing it while it's true, or skip the while and move on to the next RPN instruction if it is not true. All right? So that's how this works. If and else and an if is very similar, although in this case the comparison is done up front. So I don't wait until the while, which is the end of the loop, to compare. I do it at the beginning. So when I encounter an if instruction, I go to alpha and I look at the two parts, compare them, and if it is true, I do this chunk of the code. If it is false, I go to the thing below else, if there is an else, and if there is an else, and if there is no else, I just go directly to end if. I keep moving happily around. So the first thing that if does, as usual, is make sure that end if exists, or alternatively, else exists. Either of these two has to exist. And then apply the test and jump back and forth depending on what the result of the comparison is. All right. And this is really getting a bit weird or nerdy. This tells you which fields in the header buffer, in the buffer header, are used, where the information is stored. So for instance here, we have the register number, which acts as the marker, is stored in this field. Sorry, this one here rather. The address of the controlling instruction, like do, I have to put that address somewhere, so when you go to while and the instruction is true, I need to get back to that instruction. Same thing with the select case and the for next is here. And then remember I told you the structure gets activated until it gets deactivated when the condition has been met. So that's the flag contained into this field, into the buffer header. So the buffer header is crucial and keeps all these control fields. And what else does it say here? There's more terminology about it. How do I call the selected value or the selected variable and the selected register? It's a bit confusing, but anyway. And in addition to the header of the buffer, I told you already that I use the return stack, the RPN return stack, registers A and B, to store addresses of where to go back if things have to get back. Now that imposes a set of limitations in terms of how many nested structures can I have. Can I have if and if, and inside of them another if 3, 4, and there are some restrictions apply. Contact your doctor. But it works quite nicely. Okay, so here's two examples. The first example is the arithmetic geometric mean, which is a lovely function that should be in every calculator, not only because it's relatively easy to implement, but also because it's a great way to calculate more complex functions, like the elliptic functions. So here's how you do it. Again, it's quite short. There is an optional part here, which is the round comparison, so you can ignore that. This is just to avoid oscillations in the number of decimals. But look at that, we're talking about 15, 14 steps for the AGM. And that is gilding the lily, because here I do things that I didn't have to, like taking the integer part of the absolute value of x. I wrote this here so you see that it can be done, but you don't need to, because you can just do two RPN instructions, int and abs, right? Integer part and absolute value. But here, you have here the absolute value of the integer part of x. And then I evaluate that into either y or, sorry, it's hard for me to read. The first one is I, you see in the formula is the integer part of y, and I evaluate that expression, which is a trivial thing, into y. So I make sure that y has an integer absolute value, so non-negative. I do the same thing for the next one, for x. So I get the integer part of x, and then I get the absolute value, and I evaluate that into x. Eval dollar puts things into x, that's the standard, that's the nomenclator. So now I get a do structure, which should have a while somewhere. Here's the while. So do and while. Okay, so I got the do. I'm going to keep my own address here, because when I go to while, I maybe need to go back to myself. Okay, so I store the do address somewhere. By the way, is there any while here? Let me check. Yes, there's a while. Okay, so I'm not going to show you the ugly error message saying no bounds, because you are bounded. Perfect. So let's keep going on. I have a formula here, which is good. Oops, sorry. Which is going to do the square root, the addition of the values in x and y, and it's going to divide it by 2. If you remember, the arithmetic geometric mean is a value which has the property of that the arithmetic means equals the geometric mean. And the arithmetic mean of two values is the addition over 2. Whereas the geometric mean is the square root of the product of both, I think. So the first thing you have to do is do the arithmetic part. So this is the arithmetic part, x plus y over 2. And I put that thing into x. The next thing I have to do is the geometric mean. Now, x has been overridden by this result, but there is something called last x. So the old x has been stored into L. That's why the geometric mean uses y and L, not y and x, because x is now containing the arithmetic mean value. Anyway, so I get the square root of times y and L, and then I put that into y. And if they are the same, I just round both values, and then I go to the key point of this structure, which is the while. So again, is x different from y? Are they different? If the response is true, then it says do while, so I have to keep doing it while they are different. So if they are different, I'm going to go to, where are you going to go? I'm going to go back to the do. How do I know where to go to? Well, that's part of the buffer instruction, or it's part of the RPN return stack. So it goes back to do, and it keeps repeating the same iteration, it keeps iterating the same thing until both values equal. And we know that they converge because this is called the arithmetic geometric mean, and it converges. All right. Now, here one is the Ulam's or Collat's conjecture, which is defined by, I have a number, so if that number is even, which means the modulus 2 is 0, I'm going to get that number over 2, so half that number. If the number is odd, I'm going to multiply this by 3 and add 1 to it. So I want to keep doing that until I end this sequence. It turns out that sequence ends into 1. It may take longer or shorter number of steps, but eventually converges into 1. So let's see how to implement that with this module. I am going to call this Ulam. I'm going to do something which is not strictly necessary, because you can do that in other ways, which is again the absolute value of the integer part of x. Then I'm going to do something even more silly, which is I'm going to test for 0, which you can always do with is x. It is equal to 0, x equals 0. But here I'm going to type, really, I need a pair of eyes. I type x equals 0. I check if that is true. And if it is true, is it equal or different? Right. So if we start from 0, I stop it because there is no gain. The number cannot be 0, the starting number. So if it is 0, I stop it. And that's the end of this silly structure, just for the sake of the example. And then I'm going to say, I want to clear the register y. I started by doing that. So I say 0, evaluate y. So I put a 0 in y. Again, that sounds very silly, right? But remember, you can do that and selectively clear any register you want by inputting, or not only clearing the register, but you can input any value into any register by using this combination of 2 steps. And now we're getting to the meat of things with the do. So, all right, there's a do here. So I need to scan the code looking for a while. Oh, here we go. There's a while. So get this structure is complete. Let's keep moving. I'm going to put this address into my header buffer or the RPN stack as appropriate. Fine. So I know where to come back when I have to. Perfect. Let's move on. So next one is an if. All right. So there's a nested thing here. If it's going to look into alpha to see if the expression in alpha is correct or true or false in the Boolean sense. And this is the modulus of x and 2 equals 0. So is this a even number, right? If it is an even number, yes, I'm going to do whatever goes below if. And in this case is, I'm going to get x and I'm going to divide it by 2, which matches what the formula says here for even numbers. Perfect. Else, I did already the part, so I need to skip the else and go to the end if. Or conversely, let's say that this if was false. In that case, I will not do the following step. I will go directly to else, skipping whatever's in between. And then I will do the 3 times the number plus 1. Done. How is it going to be done? It's going to be done by the eval dollar. So I'm going to evaluate the alpha expression into x. Is that result equals to 1? If it's equals to 1, I'm done. If it's not equal to 1, so I'm going to go back to the do. I'm going to repeat it again. Et voila. Okay, so where's this? A scripting language. So we can do that till the cows come home, the whole day typing things and repeating the same. Or we can type that into an extended memory file, an ASCII file, and let the program run that file as a batch file. And it will do the calculation for us just by pressing one button. So this is the example of the gamma using the Langston's formula in the script fashion. And the script language is also capable of getting the do, while, and if, and end if. It does not do the select cases, but it's quite capable, right? I want you to see this because this is quite nice. And that is the solve program. How to do a root finding. So I'm going to spend a couple of minutes here. You probably are familiar with the solve. We're going to use the second formula, which is here, in that the next value of our guess, so we start with a guess, x0, and we calculate the next value of the root, x1. Then we calculate x2, x3, and eventually xn is going to be the root of my function. So how is the next value calculated depending on the initial or the previous one is the well-known formula of the second here, which is that one. I use the old value, I subtracted the previous value, so it takes 2 guesses, x0 and x1. I divide this difference by the difference of the functions of these two values. So let's call them f1 and f2. Basically, I do this division. I multiply that by f1, and that's the number I subtract from the initial value. So that's how you calculate the next iteration of the root. All right, so how is that implemented using the formula evaluation? We start with the formula already in alpha. So I type my expression, function I want to calculate the root for. And I have the 2 guesses in the x and the y register, x0 and x1. Or xn minus 2, as here. So we start by saying, I'm going to save my formula in memory. Why? Because I'm going to reuse alpha for something else in between. So I use STO $, which is going to get my formula up to 24 characters, boom, into data registers. I will bring it back to alpha later when it's needed, but in that way I have alpha free to use. That's what this instruction does. Save the formula. Okay, we have a label here. I'm going to evaluate the formula and put it into Z or Z. So this is going to be f of x1. because whatever the formula is an expression in x, is going to calculate f of x and put f of x into z. Then I'm going to swap x and y. I'm going to do another evaluation of that formula, but I'm going to store that into t. Remember, we have x, y, z, and t. So now z contains f1, and after the second evaluation, I have f2 into t. So I have the 4 components of this formula already in the stack: x1, x2, f1, f2. So now I'm free to type another formula with this expression because I have 4 values in the stack, and that's what this formula is about. You see, y minus z times, what does it say here? I cannot read it. This is y minus x, what it says here, times z minus t. So that is the same formula again, and I evaluate that. I say, okay, are we done? Well, first of all, like in the old tradition, I check for flag number 10, and flag number 10 is up or on. I show this iteration. But then what I do, eventually, is I bring my formula back. So I recall the expression, and I evaluate it. Ah, gosh. If they are different, so if the next iteration is different from the previous one, I repeat the iteration. I repeat the loop. I loop back. If it is the same, I found my root already. So, end of the day, in about 15 steps, I have my solver done. Okay? And it's easier to read than going through any RPM comparable program. Okay, any questions on formula evaluations and loops and do-whiles, structures? It's a futile exercise, perhaps, but it was a lot of fun. Time elapsed. Are you sure? Okay, 5 more minutes, I'm going to take over. Now that we have these, I want to go back to an old subject which was like a thorn in my back for many years, which is I want to be able to do an equation solver on the 41 in microcode. Because there are many multiple focal programs that do it, but I want to have it in microcode. So I wrote it. And this is going to be based in the formula evaluation engine, but it needs another layer on top of that. And the layer is a solver, right? Not a solve, but a solver. And the solver is going to require variables. So you have your known and your unknown variables in an equation. Okay? So you need to tell the system how are you going to call your variables, which one is the known, or which ones are the known, and which one is the unknown. And this thing is going to collaboratively work with the engine here to calculate the unknown based on all the known formulas, on the known values. And this is just another way how it works. We need a solver behind the scenes, because once we write the right formula to solve for, we need to solve for it. We just saw how to do that using the formula evaluation. I showed you the example of how to write it. So basically what this does is, all right, I'm going to tell the system which ones are how many variables I have. I can have up to 6 variables in my formula, my equation. So once I tell it how many variables, what are they called? And there's 1 letter per variable. So I can call them whatever I want, but it has to be just 1 letter. I input the number and names in a function called mVars, menu vars. And menu vars, if I am editing the software or the program, is going to create program steps for me. And it's going to do as many of these branches as number of variables exist. So if there are 3 variables, it's going to create 3 different subroutines for me on the spot. So that's done by the function, I don't have to do it. And then I just go back out of program mode and I type solver. And when I type solver, it shows me the name or the number of variables with their names. If I know the variable, if it's a known, I input the value and then press the soft key, the local label A, B, C, D, E, F. That value is taken by the system. And if I want to find out the new value, the unknown, I don't type in a number and I press directly the local label that is assigned to that value. Then it does the solver behind the scenes and it calculates it. And believe it or not, this works. And it's not using any RPN, is M-code using the formal evaluation behind it. Yes? All right, and this one here is more elaboration on how the capabilities, and there are two different MVARs. One of them is for named variables, so you have any name, you can give them to them, always restriction. Or the other one goes up to 6 variables. So you have some equations that require 6 variables. In this case, you have to label them A, B, C, D, E, F. But apart from that difference, it's pretty much the same. This tells you where are these names stored, and guess where it's going to go back to the buffer again. Buffers are such a common and such a wild card for us. And we put in here the information. If it is 5 variables, each variable name takes 2 digits. If it is 6 variables, I needed to code that into binary, but all those are details because it works the same. There is a deduplication process happening behind the scenes because nothing is stopping the user from typing 5 times the same name, right? So that would be stupid, but the program deduplicates the repeats, and also the program sorts the alphabetical inputs. So if you type things in different order, it will get back to the A, B, C, D, E in the case of the named variables. And the module comes with a pre-built library of examples, and you see here what examples are. In some cases, most of them are any names for them, any letter, and in some cases it goes back to A, B, C, D, E, which I believe is here, the quadratic polynomial case for the coefficients, and the time money, what is it called? The time value of money here, I think is also, there's also using name ones, which is quite interesting. That was a difficult one to fit in. So it required a chain calculation because it's quite a long expression. But you see here, it works. So my time is up. Is it? It's up to you guys, I can go forever. Okay, now that's when it's going to come down. All right, so that's all I have about the Visual Focal ++ formal evaluation. But there is an appendix which is inspired by the 24S, it's called 24S, and the 8 register stack, double length stack. I wanted to do the same on the 41. So I started working on that, it was done, it works. So there's another module, nothing to do with the formal evaluation or the Visual Focal ++. It's called the double down, which all it does, is an 8 length stack for the 41C, also on M code. And that one, if you are interested in microcode, is quite challenging. No, there are a very simple part, which is, okay, all you have to do is replace the standard functions that manipulate the stack, that impact the stack, like pushing things into the stack or dropping the stack. So I replace the original ones with new ones, and the new ones are aware of the new length. But then there are other actions, like I'm going to delete one number, or I'm going to input a number. I just look at the computer. Right? So what is that going to do to the stack? You type 4, and there's no flag 12 activated. That's going to input 4 into X and lift the other variables into the register. So number 4 doesn't know that now there is an 8 level stack. So it's going to go to T and it's going to wipe it out. So you need to be able to intercept anything that you do that manipulates the stack and stop the OS, the operating system, from doing what it's supposed to do before it does it. And how is that done? That's done using one of the interrupts on the 41. It's called the IO flag. So when I type 4, somebody is monitoring, is watching what's happening, and is going to say, right, I know the OS has wiped out whatever it was in T before, but not to worry, because I had the precaution of storing what was in T in a backup safety place, which is called the last good T known. And the last good T known is a register in a buffer. And then it's going to restore that and put it into T. No, T is properly assigned or readjusted by the OS. But whatever is above T and what was in T before needs to be pushed into A, B, C, D. So now we have X, Y, Z, T, A, B, C, D. Sorry, Walter, I copy. So whatever was in T, the last good T known, is going to be put into A. A goes to B, B goes to C, and C goes to D, right? So that was interesting. I had to rediscover how the stack works because we take it all for granted. And there was a tricky case, which is I delete one digit, nothing happens. I keep deleting digits using the back arrow, nothing happens. Then I delete the last digit, and then flag 12 gets, boom, activated, meaning that the stack lift is disabled because I re-input another. That was also tricky to catch or to trap, but it was done. So it's done. And with that, my friends, there is here a diagram which goes into what I said before. These are the functions that have been added to this ROM. Oh, this is something else, because the ROM has two components. One is the dual length stack, the double length stack, but it also has something called the dual numbers, which is a completely different ball game. I'm not going to bore you with this, okay? And the very last thing before I let you go, I'm really enjoying the suffering, is another module which is called the XMEM extensions, the eTwin, the XMEM twin, the extended memory or the extended functions twin. So we know how the extended memory and extended functions work. So in terms of the memory, you can have different types of files, X number of files, ASCII files, data, program, etc. But what if all you want to have is individual access to all the registers in XMEM? So forget about the XMEM structure as HP invented it. All you have there is a block of memory, and I want to use that block of memory as I do my main memory, doing store, recall, swap the registers into my X pile. Let's call it the X pile, okay? So that's it, that's what this ROM does. So we have 605 registers that can be accessed individually by the functions of this module, using recall, store, swapping, etc. That's it. All right. Thank you. We have one question.
The AGM, I saw a paper a few weeks ago, generalized AGM, which is a function which contains AGM1, AGM2, what we call AGM2.
Right, yes.
I don't want to ask anything to you, I just want to inform you it's on my to-do list to have a look in it, because it's not written today, it's too fresh. I just wanted to do it when I have a bit more time, but it could take moves. Just for you to know what generalized AGM is. Right.
I can give you a head start. The AGM is the standard arithmetic geometric mean, and the AGM2 is a construct, is an artifact that the mathematicians have developed to be able to calculate the elliptic functions. I think it's the incomplete elliptic function.
But both together are
both together.
Another function.
Yeah, because the function that they belong to is the incomplete elliptic function.
But they are both the AGM2 is
AGM1
a special case of AGM something. So
yes.
There's a bigger one, but bigger one I just wanted to
and I don't know where you saw that, but it's probably in the sand math. In the sand math, that's where they both are, and that's how they are calculated.
I spent a few days and I discovered what we did on it. So, but it's on my to-do list.
Okay. Enjoy. All right, guys, thank you very much. I appreciate your attention, and happy to be back when you call me.